Okay, so good afternoon, everybody. So I'd like first to thank the invitation from Manuel Barral and the organization. It's a pleasure, my first time in Uruguay. Actually, someone mentioned that's first time out of Brazil in South America. It's the same for me. It's weird. I changed a little bit the title as I actually added some other initiatives that we developed that I thought would be of interest to you. So I have to do this. So, okay, so that's where I come. So I work at the National Laboratory of Scientific Computing. So I'll briefly give a view to you what we do. So we are a research unit of the Ministry of Science, Technology, Innovation, Communication. So the ministry has different unities, thematic unities, and our research units. And ours is a computational modeling. Computational modeling used to be mostly having first-based principles, physical-based principles analysis or modeling of natural phenomena. So doing partial differential equations and then eventually simulation natural phenomena somehow. That's how it was initially founded 35 years ago. And then it's extended to other areas, and in particular, so actually this comprises mathematical modeling and computer science, this computational modeling. And we do have offer a graduate course in computational modeling. That was the first one in Brazil to offer that course. We don't have undergraduate students, but we do have master's and PhD students in this program. We are a national lab, so we coordinate many initiatives, federal initiatives. So one of those is the National Center of HPC Systems that are distributed in the country. And we also have coordinate two National Institutes of Science and Technology. So the first one, MAC, is computational science support to medicine, which kind of very somehow aligned with this audience. And the data science that I coordinate, the National Institute of Data Science that I coordinate in Brazil. And then within LNCC, we have some thematic, again, laboratories that narrow down a little bit the area of work. And for this audience, I listed three which can be of interest, so, and eventually thinking about possible collaborations. So we have LabInfo, which is a very important bioinformatics laboratory in Brazil that offers sequencing services for the whole research community in Brazil. Various courses during the years that have been, people that have been formed in bioinformatics by our bioinformatics group. We have also EMOLab laboratory that do cardiovascular system modeling. So this is people doing, again, physics-based modeling of the human cardiovascular system. And actually this is associated to one of the things I will discuss with you later. And I coordinate the Data Extreme Lab, so it's a lab that interested in big data in general, but I'll go a little bit further in detail in a minute. So this is the picture of the facade of LNCC. LNCC is placed in Petrópolis. Petrópolis is a town like 70 kilometers from Rio, up in the hills that are close to the city. That can be reached very easily by road, but there is an airport in between the city and LNCC. So it's a very convenient place. Actually, students get somehow isolated so they can concentrate in their work. So it's a very good atmosphere. Yeah, so Rio is tougher, but Petrópolis is less thing for them to do, so they can do their work. So we do have a supercomputer. So this is the largest supercomputer in South America. So when we actually installed it back in 2015, it was in the list of the top 500. Then very rapidly it went off the list. But then we just upgraded to 5.1 petaflops last month, and it's back to the 193. So this number means that it can achieve a peak performance of that many trillions of floating point instructions per second. So it's a huge thing, right? And that means that it's the 193rd powerful machine in the world. So it's a very competitive machine, and is completely available for the research community in Brazil. So what we do, part of that Sinapad initiative that I mentioned, is to offer that service. So if you are in Brazil and you need computational power for your application, then you can apply for that. That is under calls, so there are calls that are open and people can submit their projects and eventually get some share of this machine. And the lab I coordinate is the Dexel lab. So we mostly have 3 areas of activity. So one part of our activity is in AI, and that AI means mostly modeling. So build up machine AI models, mostly deep learning, but there are others machine learning activities, but to a certain problem. So targeting certain problems, doing classifications and things like that. There are images, there are spatial temporal classification, regression problems. So I call that mostly a modeling problem. So it's similar to the physics basic principles modeling, but now looking at data. So data-based modeling in some sense. We also build systems to support, so one of the activities we do methodologically is to provide tools that help people do their work. So in the AI scenario, we are developing a system that actually does what people call the auto-ML, so enable to automatically select the best models to do a certain prediction. And when considered, for instance, spatial temporal predictions, this becomes quite tricky problem. And then we are working on a system to do that in cooperation with Petrobras. Then there is the area of big data processing management. So these are what I call there is development of algorithms for processing huge amount of data for a particular target. And we have different collaborations going from medicine, public health, and astronomy, sports, which I will be mentioning in a while. So, and using like big data kind of frameworks like Spark and things like that. So how can you actually solve problems, large problems in this infrastructure? And then on the right-hand side, there's more statistic-based approach of data analytics. So more people would call now data science. And then we have mostly there is the cooperation with Fiocruz that we actually have one what we call big data platform for health, which is available for the community in Brazil. I'm not going to talk about it today, but it's actually bringing data from DataSUS. DataSUS is the Ministry of Health data system that hosts the whole data linked to the events in health that the ministry is aware of, and then getting that data, curating that data, and making it available in this platform that actually scientists can eventually browse using a nice like dashboard interface, or they can build their Python or R notebooks. So we have this infrastructure where actually the curated data, which takes a long time, as someone had mentioned. I think some of my previous colleagues mentioned, eventually 2 years to get this data ready for access. So this is the general picture of what we do. And so in this talk, I will try to convey this idea of these modern information systems. I think somehow this is what we are doing, trying to face the challenges that these different modalities of data and different kinds of models now are put together to solve problems, right? So we have images, we have quantitative data, we have network data, web data, social network data, and how to put this together eventually to produce some knowledge. And also, in addition to that, dealing with models. Models in both have machine learning models, but also simulations. So as I told you, I mean, this cardiovascular system is a model that brings in information from the physics knowledge, and how to actually add physics to the machine learning data is something that we're looking at as well. And eventually get to this knowledge. So there's people that already mentioned this idea of knowledge base, which is an extension to the database view. So database is most a data let's say, logical view of information. But knowledge base is something more. Knowledge base is about linking, associating the data, and giving some meaning through these associations, to the annotations, and being able to infer new information from what you have. A lot of work in this embedding areas of learning what you know and then inferring new knowledge in the graph. So we work in some sense in this spirit. We're not there yet in the sense that there are a lot of holes in this process, but this is the target we're looking at. So the objective here will be in this talk would be to present these initiatives that we have had in integrating. So we've been seeing integration problem raised before, so we can rephrase those problems. But actually looking also to methods. So I believe a lot that data and methods are very similar. So when you talk about the machine learning model, you're mostly seeing you are concerned about the data it produces. Eventually the data it consumes as well, but the data it produces. From the data perspective, you can see it as data. Data of a certain kind, with certain uncertainty brought by the actual model, but it's data. So if you put that together, you have data of different modalities, including data produced by models. So the outline of the talk, I had added 3 systems, but then I rehearsed this morning and I was kind of going through my slot of time. So I'm talking about 2 systems. The SARA system, which is the sports, which I had announced, and the SAVIM system, which is actually coupled to the simulation. So give you some hints on that as well. And then I go to final remarks. So the SARA system was an initiative that we developed together with the Brazilian Olympic Committee for the Olympics in Brazil, the Summer Games in Brazil, 2014. So the idea is to put up a system that could help improve the performance of athletes. The athletes that they have already identified as candidates for medals and so on. And in long term, to improve the performance of also new talented youngers. And the challenge on that, so there are many, it was an initiative that was essentially multidisciplinary. So we were talking about with biochemistry people, biomechanics, nutrition, what do you call behavioral specialists, training specialists, physiology specialists. So all those disciplines would be looking at the athlete and trying to understand how that particular athlete behaves. And that's somehow the link to this meeting, because the athlete is very individual. So you cannot offer suggestions for athletes in general sense. And this brings a lot of challenges as a first step. First of all, if you think about machine learning, it doesn't work. Because machine learning is basically about generality, how you can generalize what you learn, right? And if you want to do some specific suggestion, so how do I get that athlete to run less than 2 hours marathon? What I should interfere, where I should interfere. Well, when I say it doesn't help machine learning, it does, obviously. It's just that the traditional way to do it, it doesn't. And we are investigating that. We're going to get to this. Also, another important aspect is that we look at through time. So we want to see this, and what we wanted to see was also varied. So depending on the disciplines, people are interested in looking at different things from the athlete. And this could also vary during the follow-up. So you could not develop a system that you say, so you have variables X, Y, and W, and that's all. And then tomorrow I find that there is something very interesting, some publication that came up showing that other aspect is important to be observed. So we wanted to be the system to be extensible so that you could add new what we call observable elements as you go. And then kind of following longitudinal through those variables. Okay, so SARA system has this perspective of so some colleagues in the project call that sportomics. Sportomics is this combination of these different areas, looking, having the focus, the athlete. But putting this together was the SARA system. So what we would do, we get different sources of data, like sensor data, so put the athlete to walk and see how she would step. You understand whether this can be improved, so having like a continuous points of in this moving IoT moving object. We can also see how actually she is doing while running. So is there a possibility of reducing this 2 minutes from 2 hours by just looking at her biomechanics? How she bends over when she runs, how she moves her arms, how she actually enlarges her steps throughout the exercise. But also, like, biochemistry data, getting blood collection. So you collect data from the athlete, and then you're going to analyze it through the exercise. So one of the things about the athletes is that there are two interesting things, but many interesting things, but two that I would like to emphasize here is that, as I said, so it's very individual. So all the values that we call reference values that would be used for you in your hemogram is not useful for the athlete at all, because in the areas where it actually excellent, in the area where they are expertise, their values of reference are far away from the normal people. And these values people don't know. So this is one of the things that people try to figure out. So how can we identify the pattern of that particular individual, and where are the limits, so that you don't overtrain that guy so that he breaks, and then you don't want that to happen. So what's the upper bound and lower bound of each individual, and various others information. So there's a huge data model, and this is just things for us to look at, highlighting some aspects. So in the system we have something that's target, because we both follow up athletes and teams. So you can look also some collective variables, so the team, how it behaves through time, and try to improve the measurements for the whole group of people, or individual ones. And then this is done through what they call evaluations. So evaluations occur during the preparation, so they have what they call the Olympic cycle. The Olympic cycle is 4 years, so all the preparation go into during these 4 years, and you have to be very attentive, so that you have a curve that tend to increase in the performance, and at a certain point of time you cannot pass it over some boundaries, because then you have injuries and things like that. And the observable elements is the key thing. So you can add what you think about that should be observed in that box. So you add that an observable element is already operating in the whole model that we have implemented. And we have also something that's called a routine, and a routine is to express how in which situation is the athlete. So if he's in intense training, so it's expected that the values of observations in certain variables would go up or go down. So there is a semantic correlation between the actual exercise that he is involved and how you expect that state to be. So you want to register, also identify these different steps. And we did that by modeling trajectories. So we have two kinds of variables, mostly like observable elements, what we call the continuous and discrete. And continuous are those that you want really to follow up and draw some interpolation and sort those as curves, so that you can see how actually the behavior is evolving through time. And the discrete is actually points in that spectrum that tells which certain events that are not followed up in time, but you want to know that they occurred. For instance, they have been administered some kind of medicine. So we want to know when it was and what it was. So these are discrete variables that we can also record. And then the system is running. So there is a real. So this whole project was done in what they call the Olympic Laboratory. Olympic Laboratory is a laboratory in Rio de Janeiro, with 1,400 square meters, in close to the Maria Lake, where they have the swimming competitions during the Olympic Games underneath the swimming pool. So these guys are running this process, and Saha is running there. So we do have the data from the athletes being recorded in this fashion. And then this is used in different ways. It can be like using just looking for some statistical momentums and look at how they behave, some means, some standard deviation. So what do we expect that observable element to vary? But you can also have some curves and identify how they behave and trying to cluster these curves so that you can infer those reference values for each of the athlete. But also you can use that and it's being used to try to identify talents. And talents are identified when in this perspective by the curves that are subsumed by the curve of a very good athlete in the discipline. So you can actually compare how different athletes behave and how their observable elements behave while they are, for instance, in a very intensive training exercise. And then you can also see this through the different states, as I said. So there is this huge harmonization. So the previous speaker mentioned, so that was one of the problems we had. So I was quite glad to see your talk, very interesting, because exactly, so when you put together all these different heterogeneous data, how can you make sense out of that? So that was a huge work that the specialists had to do to normalize the information and to wait so that there is some, I'm not completely confident that they done their job there. So there are certainly lots of things that don't make sense. And yeah, so there is a huge methodological work to be done once this data it's put together. But here, so once this is done, and if it's done correctly, so you have this whole bunch of data that reflects each individual. So what can you do with that? In terms of, for instance, in the athlete, obviously what you want to do is to improve her performance, right? So here is an example. So we're looking for this marathonist that wants to run to reduce her running time in 2 minutes, as I told you before, right? So what that group would do before our work was to raise hypotheses. So hypothesis could be, okay, I would increase training. I will try to increase the VO dose, the breath capacity of the athlete. Or improve the step. Or I will better hydrate the athlete. So there are many hypotheses that you can think of. But how can you prove those hypotheses? False or true? Well, now you have evidences. So you have the observations that have been captured through time for that particular athlete. And by having that evidences, we would like to narrow down the initial hypothesis to a couple of suggestions, which would be where you want to interfere in the athlete. Well, this turns out to be a machine learning problem. So I told you that machine learning wouldn't help, but that's not the solution. But I will talk to, so this is the general idea. And the general idea is that you want to build a function that maps the athlete state to a certain value. That value is, for instance, her performance in the 800 meters. So you like observe the athlete in a certain stage, and you put her to run 800 meters, you register the time she did, and you do it through time. So you start learning how that state presents and the relationship of that state to the actual result. Well, for a machine learning model to work in these conditions, you'd have to have millions of those. And we don't have that, obviously. So that's why I said that this wouldn't work. And it didn't. But it sets the basis for what works. And this is what we are working on. So another thing that's also interesting before is that even if I had that, that's not what I wanted. Because I wanted is an inverse function of that. Because the point is, I want to achieve that goal, for instance, running marathon in 2 hours, so how should I be? So I want to do the reverse path from where I am and where I'm going to be, right? And this inverse function turns out to be more complicated. because it's not a function, first of all, it's a relation, because it's a set of elements that you want to bind. So we are working on this, and this is comes out to be a optimization problem. So if you look at this, it is y here, and if I am here, so this should be another slide, so sorry, it should be something here. But anyhow, if this corresponds to the state of the athlete, and this is where I want to be. Now, sorry, if this is the state of the athlete, and this how fast I would run, so the difference between this and actually the time I would like to achieve is actually an error of prediction. And this error of prediction is produced because your state is not correct. That's not exactly the values of states to produce that outcome. So this becomes an minimization problem, so that you want to minimize the error with respect to the actual target by changing your parameters here. So this is what we are learning now. And actually, this is a much more general approach. This is a general approach for learning a small amount of data. And this is very particular to this audience, because, I mean, for the patient, you have the same problem. So that's what I mentioned. So we are building now the AI layer on top of Saha, and it's mostly doing this thing that I mentioned now. That's not yet. So this is the PhD of one of my students. So the Saha system is entirely functional. It's working at that lab. So we gathering data. It's very secure. So it runs in a secure room, so no one can actually access it from the outside. You can imagine these athletes, you know, our top athletes' data, you know, biochemistry data, biochemical data, and so on. And that's it. So this is what I wanted to how much time I have? Just 10 minutes. Tough. Okay, so I try to give a short version of Savimi. So Savimi is another project that we developed within the DEXL. And this is, again, so the interest for this community might be that, you know, the cardiovascular system is that is being developed by the EULAC Laboratorio is obviously something that's important. And in this case, we do, for instance, the simulation of the complete simulation in 1D. But you can see here is actually an aneurysm. An aneurysm that in a particular, so this is a 1D simulation of the cardiovascular system with a 3D simulation of the aneurysm. Oops. I don't know whether it's going to work. What should I do? Yeah. Okay, so it's not a big deal. It's just that, so there is the actual simulation. So the simulation can be seen as the reflection of certain behavior through space and time. In this case, you have the space which is given by a mesh representation of an arteria, including the aneurysm, and then you're going to simulate how the blood flows through the arteria through time. And the interesting thing here is that you want to see whether that aneurysm might burst, for instance. And if it in certain point it might happen that will give to that condition, this can be very serious. You can imagine a brain aneurysm, for instance. So these colleagues tell me that this happens, so out of 10 surgeries in the brain aneurysm, only one should be really done. They just don't know which one of the 10. So they do the 10 surgery interventions. So the idea of the simulation is to help the physicians to decide which one, for instance, in this case, to interfere. And in our case, what we want now is blocked. Okay, so there is another one. It doesn't matter. So what we did is the following. So in all simulations, so from the system point of view, the simulations produce huge amount of data again. So these are thousands of files that are produced during a simulation. And actually what you want to see is what happens within that aneurysm region. And this is a spatial time, so you want to to specify like a query, give me what's going on in that particular region of the simulation. I don't care about the rest. So if you need to do that by yourself, you're going to write, and that's what people do, they write scripts, like Python scripts or shell scripts, that you traverse these thousands of files looking for the aneurysm region, and eventually do some mathematics, like they want to know what's the maximum pressure through time that it suffers, so to see whether the wall of the arteria would sustain that pressure or not. So this can be actually done by queries. So our intention by developing Savimi is to couple that system into the simulator so that the user, the actual scientist, can express like analytical queries on the data produced by the simulation in real time. So the idea is that the simulation is running in Santos Dumont, the supercomputer I talked to you about, and then the data as it's produced by the Santos Dumont computer is chopped up to Savimi that actually waits with a query that the scientist has expressed. So the scientist just says, okay, I want to see what happens in that region of geometry space through time, and I want to see whether the blood pressure gets to the certain amount. So this is a filtering and an aggregate query. And if you can also do like, so we have this functional query language. So Savimi is something like this in terms of data. Is a multidimensional array model so that data is represented through a multidimensional approach. And why is that interesting? Is because natural phenomena occurs in space and time. We are usually interested in modeling it. It's also useful for machine learning. The ones that work with machine learning knows that you have a multidimensional feature space that you want to explore. So the data representation is quite suitable. And this big matrix is actually split automatically in sub-matrices so that this processing can be done in parallel. So if you're processing thousands of files, you don't want to do it scanned sequentially, you can do it in parallel and so on. So, so this is an example. So this is a simple query. So this query, what it's doing is getting two simulations, and it's looking for the simulations and trying to, so these are two different arrays that are being produced. And eventually, it's trying to compare and compute the average of the outcome for each position in space and time. So by just expressing this, you might be processing like hundreds of thousands of files, combining these different simulations to get an outcome. And interesting enough is also that you can put on the top this new function catalyze that produce the visualization. So the idea is that not only the scientists can express queries that analyze, does this filtering or aggregate operations, it can also directly produce the files that can be seen in a visualizer like ParaView, which is used in this context. So the idea is that the physicians could be seeing the simulation as it's running, and then take the decision. That's what we want, see what it's going to do. So these are some results, blah, 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 not getting that. So Savimi takeaway. So Savimi is a system, so it's a fully functional system again. So it's being developed, it was developed during the PhD thesis of one of my students. We are extending this now to, so the initial motivation was what I put this in this context. Now we are using this as the basis for some operations in a machine learning context, like selecting models, as I mentioned to you. So if you have competitive models, which one to pick? This is a very, very interesting problem because people are starting to produce machine learning models and so on. And what happens is that eventually you have, and one interesting thing is that people, that when they train the models, they have some error, they compute, what they call the generalization error. But this is a single aggregate of the whole training. So imagine if you have a model that predicts something in this room. So I can easily think that some of them would be very good in that corner left, and others would be very good in the corner right, or even in the center. So the quality of each model varies within the multidimensional space. So so in this application of Savimi, again, we see predictions as data. So you ask queries that include the running some predictions, which includes selecting the models that would be used for the predictions. And these selections has to be just take into account the multidimensional space in, that your input is considered. So this is something that we're doing now. To conclude, so I present you two tools that we've been developing. So as we've seen before, so identification of personal characteristics embodies, getting multimodal data from different sources. In this case, we mostly talk in Susaha, mostly at this point work with quantitative data. But we want to add, for instance, imaging. So I mentioned before the problem of field data, right? Training with field data. So I told you that that can be eventually solved by using, applying some optimization strategy. But another thing that you can do is to add more types of data that complement the data that you have. So if you have more, if you have images, for instance, add it to the training set. There is multimodal learning that's been applied. So this multimodal learning here, so these are the things we are looking at now. Learning with small data in general. Applying multimodal learning to extend what I can within this multimodal context. Now, add physics integrated learning. So this is very important as well. So I didn't talk about that. So this is another line of research that we're doing. So there is the fundamental problem in machine learning is that they think that you don't know anything about the problem. Only the data tells you what you know. And that's not a fact. There are huge knowledge that exists. And this knowledge should be integrated in the learning process. This is called model teaching. Model teaching is the means by which you add some information to the learning process. So, for instance, in physics, there are some laws that cannot be neglected. So the data, you cannot go through a space where that physics law will be refuted, because you know that's right. So how to add physics constraints in any kind of constraints within the learning process. So we're working on that as well. And then automatic selection of spatial models, as I mentioned. So this is the Dexel team, I think partially, almost there. I'd like to acknowledge CNPq, Petrobras, and INRIA, that are our collaborators. And obrigado.
I have a quick question. Yes. I need a mic. I can try it out.
No,
we do for the
yeah.
video.
Take this one?
We can share our mic.
Yep.
Okay. Thank you for your presentation. Congratulations. A lot of work. It looks like a lot of politics involved as well. Anyways, so you were saying that with the runners, you were using the data produced by them to try to improve them in the machine learning algorithm.
Yeah. So the data that collected the data from the athletes, right? So the athletes, in the general sense, we have the database that collects data from all athletes. Then you can stratify this by discipline. So there are some cases that don't make sense to combine, like a volleyball player with a swimmer. So there is this stratification. But again, this is not enough. So you cannot kind of collect blood samples all the time from the athlete. You collect it once each week. So it's never going to solve the problem for the learning process. That's why we're looking into the other part, yeah.
Well, yeah, so my question was that if you are saying, well, we don't have to use machine learning in the traditional sense, we have to use it in a different way so we can have more personalized treatments, right? So we have this athlete, and you are just getting samples from this guy, but we all know the garbage in, garbage out, right? So how is this gonna learn or improve?
Yeah. So okay. Yes.
So,
sorry, go ahead.
But I think, well, after what you said about the physics, maybe you can try to optimize or make an optimization model out of the data you have from your athlete,
yeah.
but
yeah.
still.
So, well, anyhow, don't get okay. So the point is, how can we get more data without having, how can we get more data and such that that data makes sense, right? So in practical sense, we cannot actually collect more data from what we have from the athletes, right? So this is a constraint. It's a physical constraint. We're not going to have that. So a simple way to do it is to simulate data. You know which observations you are interested in, and you can actually simulate the production of more data. The problem is that what you simulate must be consistent with what the athletes would present. So the idea here is to what they call use a surrogate model. A surrogate model is a simpler model that you are sure that's correct. So it's not generalizable because it's only observe fewer points, but you know that's correct. So if you have a surrogate model, now you can evaluate whether your data expansion is coherent or not, and use the minimization problem to fix that. So this is the whole engine that we are working on.
Yeah, well, but again, I mean, my example was, for example, I definitely have a bad eating habits.
Right.
If I'm going to use a model using only my habits, I'm going to be the whole messed up. I mean, how do you improve that? But probably if you add some optimization to that, probably will improve. But otherwise, I think, I mean, you have garbage in, you will have garbage out.
No, but the point is we're not going to have garbage in at all. That's what I'm saying. So our process is exactly to avoid having garbage in. Obviously, you're completely right. If you have garbage in, then you're going to learn from garbage. What I'm saying is that we're not doing that. We are using this surrogate model to fix what could be garbage.
Well, we'll probably talk about it later, but
yes.
Yeah, thank you very much.
Yeah.
Thank you for the presentation. My question is, could it make sense to use as y in your function instead of the time of 800 meters or so on, to use like some other outcomes like resistance, speed, power? Because in this way, maybe you can mix more and use data from more multidisciplinary sports.
Mm-hmm. Sometimes these variables that you mentioned are observable elements that they are interested in. What are the inputs? So it depends a lot in what is input and what is output. Sometimes, so velocity, for instance, is one of the elements that they observe. So a runner, you want to observe how fast he runs and so on. But I mean, the whole idea is that this mapping function is, in general sense, abstract. So as long as there is a correlation between these dependent variables and the independent variables on the left-hand side, then you can eventually learn. And then if there is no correlation, then you're not going to learn, right? So this is most the general principle.
There was the question here.
Beautiful and interesting work. Can you share with us what worked?
What work?
Yeah.
In which part?
In all the parts. You skip some of the slides of the results.
So you want to see that?
Yeah, I want to know what
so
worked.
Most people are not interested in that. So, okay, so let's go there.
How athletes became better and...
No, this we haven't gotten at all.
Okay,
no.
So
we haven't improved any athlete by doing this. So, no. Not yet. No, because exactly this part is where this new AI comes into the game. So far, so that you mean you have to build a castle, and you build a castle from the structure. So what I talked about to you in the Saha system that's running currently is basically the basis of this structure. Once you have the data, and he mentioned that, and eventually you have good data, then you can think about having a good model. But that's the first step, and getting that,
no question.
Believe in me, is tough. But I mean, so no, I don't have any improvements at all in any athlete by doing this. We expect that eventually we might get there.
Okay, and with the other works?
The other work, yes, this is easier because this is computer science, right? It's not humans. So actually, this. Yeah, there are a lot of technicalities, but anyhow, So one of the challenges in this, so if you're running a simulation, you're running the fastest you can in your computer, right? So you want to run it fast, and you produce a huge amount of data. So current technology, actually when that actually exists to analyze this kind of data, requires you to transform the data as it is received by the targeting system. So this is, for instance, CyDB, is a system by Berkeley people. So this transformation, when you're talking about big data, may take hours, right? So this is not viable for this application. So what we do is that we don't touch at all in the data. We accept as it comes. So if you have your simulation, I can plug it in my system tomorrow, because it's just to comply with some APIs, and then because I accept the data as you already produce it. If you today have a simulation that you write your data to disk, I'm just going to say, okay, write it to this API, your chunks of data. And then this is actually counting the cost of obtaining the data that's available to analysis. And the green thing is us. The blue thing is the competitive system. And I think is, I don't know, reddish one is actually file system. So NetCDF, if you just don't have any of the structure that I'm talking about. So just to have a baseline comparison. It's obviously better than us because it's just a file system, file library, but we are not far from them, so we are good. And here is again the same comparison against the different, and also there is a problem with sparse and dense data. But I think I'll take that offline because I have to explain details here. It's just that sparse is more difficult. If you have, you can imagine that a matrix, when it's dense, you know which pointer, you can index that pointer because each point is filled up. Whereas it's sparse, there are few scattered points, then obviously you don't want to store the spaces, so you actually store the individual instances internally indexed. So there are technicalities that make the finding the aneurysm more difficult, more tricky. Yeah. Yes.
Thanks. So my question is about Saha, I think is the name. So you tell that you use an inverse function that minimize the error based on what you want to produce.
Right. Yes.
But
yes.
What is the difference between this and traditional machine learning? Because all of these models are based in minimize an error function.
Yeah. But what they are doing is that minimizing the error function for training. So you have a model. So you want to know, the parameters of your model, and actually use some gradient descent, something like that, to navigate the error to the error space, right? Now, what I want to do is not this. What I want to do, oh, sorry. I have to go back a little bit. Here. What I want to do is to fix this, the input to the function. I don't want to obviously that when you train a model, you improve in the model itself. What I want to do is not that, is to improve the input, because the inputs that might be wrong. So the input would be like this, okay, so the guy would achieve that 2 hours when the cardiac frequency is 110, and the blood pressure is this, the glucose is that, and so on and so forth. So this would be the state that the athlete should be in order to achieve that goal. But that state, I don't know. So what the minimization thing is doing is trying to improve the target value by changing the input. So
okay, produce a set of variables, value of variables that will produce the minimum error.
Yes.
But why you don't use another model to produce that value as an input?
We can talk about that later. Yes.
Yeah, she's putting it up.
Have you compared it with a stepwise regression model that you put out and then you have entry one stepwise?
But comparing what exactly?
These variables.
Wait a second, please.
It's like a stepwise regression model that you put all the variables that you wanted to, and you predict what is the best is a prediction, just to compare, because if you have speed, blood, and everything, some way other has, and then the model has more power, take one variable. That means you'll be having a predicted curve.
Okay, okay, may talk to all that later.
Okay.
Okay? Thank you.
So thank you very much, Dr. Porto.